Thank you for the introduction, and it's great to be back at PIMSA, and it's nice to see old friends and making friends here. So there's a big spectrum of people in terms of familiarity. So I think what I'll do is I'll basically try to give an overview of interesting stories, and I'll tell you 3 stories that connect with each other. So I'll start with one that is the most classical one, which is the story about the Laplacian spectrum. And by the way, for the whole talk, everything is, the theorems toward the end are joined with Otis Chodosh, and a standing assumption that I'll be using throughout, so I don't have to state it over and over, is that Mg will be an n-dimensional Riemannian manifold, which is going to be closed, meaning compact, no boundary, and connected. Just to make life easier. So, okay, the first story is that of the Laplacian spectrum. Which, just as you know, it looks like a collection of eigenvalues for the Laplacian, the first of which is the trivial one corresponding to the constants. And then you have a non-decreasing sequence of them, which go to infinity. And each eigenvalue is repeated, or rather occurs dim occur Laplace G plus lambda p I many times. The corresponding dimension of the eigenspace. So these eigenvalues, also for later reference, for example, you can compute them quite explicitly. And the example that is closest in nature to what I'll need later is on the round sphere. The eigenvalues are just given by this explicit function of p. Okay. All right, so here's a theorem that gets this story started and gives us a variational characterization of the eigenvalues, and it's attributed to Courant, Fisher, and Weil. It tells us that rather than just trying to figure out when this is non-trivial and arranging them in order, you can solve the following min-max problem, that you can recapture lambda p as follows. You start by looking at arbitrary subspaces V of the set of smooth functions with dimension p plus 1, and it's a subspace. Okay? So for example, for lambda 0, you look at lines in C infinity. For lambda 1, you look at planes in C infinity, and so on. Now for each such guy, you look at the maximum among all non-zero functions in V, and you look at the Rayleigh quotient. And for every p, 0, 1, 2, 3, and so on, this captures the corresponding eigenvalue there. And in fact, because of elliptic regularity for the Laplacian, we know that this inf is not just an inf, it's actually a min. You can attain this. And so by elliptic regularity, implies that inf is min. And therefore, you can find an optimal V. Let's call it V sub p and the corresponding optimal u. And it's actually going to be u is going to be a critical point of this functional over here. Let's call it q of u. So an optimal v and an optimal u, and u sub p is a critical point of q, which if you take the derivative of that functional and you write down what it means to be a critical point, you'll see that it's just the eigenvalue equation. So minus Laplace g of up is lambda p up on m. And because of how you've chosen this, this eigenfunction u sub p, you see that it certainly modulo this v for which it's a maximum, this v sub p for which it's a maximum, for all the other directions it's a minimum. Okay? And it minimizes q modulo v sub p. But we can do a little bit better. It doesn't just minimize modulo the p plus one dimensional subspace p, v sub p. If you look at this q, it's dilation invariant. If you scale a function, then the value doesn't change. So in fact, if you can also take a slightly smaller subspace than this, you can just look at everything that is orthogonal in the L2 sense to the span of this. So you actually minimize q modulo a p-dimensional subspace, not just a p plus one dimensional subspace. Okay? All right. So once you have this list of eigenvalues, you can start to wonder how they behave, for example, as p goes to infinity. And the theorem now that I want to mention is called the Y law. So first, I'll attribute it to while, and then there's relevant generalizations. Well, I'll call it the Y law, which says that lambda p is asymptotic to a specific constant, it's a dimensional constant, times the volume of the manifold to a suitable power times a certain power of the parameter p. This twiddle just means that if I divide this by that and take p to infinity, I get 1 in the limit. Okay? And this is just a dimensional constant. Later I'll call it alpha sub n. But okay, once you can prove something like this without even knowing what the dimensional constant is, then you can compute lambda p for your preferred space. And I wrote down the round 2 sphere earlier. You can compute it for an n sphere, you can compute it more easily for an n torus, and you can find the exact value there. So I dug it up for you. Just 4 pi times the gamma function to some power. It won't be relevant, but my point is you can compute it in a model space and you can find out what that constant is. Now, there's many approaches to proving this Y law. The original approach due to Weil was geometric. Weil. And what he did is he noticed that you can prove this by subdividing your manifold M into tiny little cubes and doing a nice additivity argument. So subdivide M into tiny things that are approximately cubical. However, there are other approaches that are analytic in nature. And one such approach is to play around with the Green's functions This is due to Carleman, from the Carleman estimates. There's another approach with heat kernels due to, okay, this is going to be long, Meenakshi Sundaram. And Plajo. Oh. And the extra juice you can squeeze out of the analytic approaches is that you can take these ideas and you can prove things about the remainder term over there. Okay? So there's the following refinement of the Weil law. Which I'll attribute to a few people, Levitan, Avakumovich, and Armander, who proved that if you subtract this from that, so if you look at lambda p minus alpha n vol mg to the correct power times p to the correct power, then what you're left with is big O of p to the 1 over n. So there's a strict improvement over there. However, the only approach we have for this is analytic inspired. So all these guys had analytic approaches. Okay? All right. One more thing to this story that is worth mentioning is that in this whole field, there's a question of quantum ergodicity, or quantum unique ergodicity. Where you start with your M, and you say, if M satisfies something, and you have a sequence U sub p of eigenfunctions, which is orthonormal then does the measure up squared d mu g, the limit of these measures, equidistribute? So is this limit a multiple of Liouville measure? Of just the of the volume measure. Now, okay, this is not going to be true in full generality, which is why you want this question over here. So one assumption people make to prove something like this is if mg has geodesic flow, which is ergodic. So this rules out things like spheres. Okay. All right, so what do we know in this situation? We know the following theorem. We know that, and this is due to Schnirlin, Colleen de Verdier, and Zeldich, we know that the answer is yes up to a subsequence. So this part is called quantum ergodicity without the unique part. We know due to Lindenstrauss and Sundararajan that the answer is yes for certain two-dimensional hyperbolic surfaces called arithmetic. And unfortunately, I can't mention everybody. This is a huge field, but I'm just giving you the highlights. We also know that the answer is, actually, it's not, it's known to be false for certain manifolds with boundary in R2, in the billiard setting. So no for certain domains, Euclidean domains. This is due to Hassel. And we know that also due to Dyatlov, Jin, and Nonnenmacher. That the answer is partially yes, meaning the limit is might not, we don't know if it's a multiple of the volume measure, but it's a fully supported measure. For negatively curved 2D surfaces. Well, surface. Okay, so again, the setting here is you have your eigenvalues have eigenfunctions, and you try to take an orthonormal sequence of eigenfunctions. You try to take a limit, and you want to ask whether the limit of that measure is a multiple of the volume measure. Yes.
What does it mean by the convergence analysis?
As measures in the weak star.
Convergence measure.
Yes, in the weak star sense. Yes. Yeah. So this question about whether the limit of measures converges to something nice or what it converges to comes up again in the subsequent story. That's why I'm mentioning this here. All right, now to end this first story about the Laplacian eigenvalues, I'm going to end with an observation that I secretly made earlier. But it's good to see it at least twice. So here's the final observation here. And it's that, as we saw, the Rayleigh quotient Q is dilation invariant. Okay, because if I scale a function, the numerator and the denominator scale the same way. So in other words, Q of lambda times U is equal to Q of U for all non-zero, not everywhere zero functions U, and non-zero multiples lambda. So in particular, instead of trying to think about the whole min-max setup as being something about subspaces of C infinity, you can do the following. You can try to replace C infinity with C infinity minus 0, and then take this quotient with R star, in which case your P plus 1 dimensional subspaces your p plus 1 dimensional subspaces get replaced with copies, well, okay, copies of what, where. So if you take this quotient here, this you can check is homotopy equivalent to an infinite dimensional real projective space. And now viewed in here, your p plus 1 dimensional subspaces, removing the origin, quotienting by r star, become linear copies of p dimensional real projective spaces. The picture to keep in mind is that, if you were looking at p equals 0 or p equals 1, let's do p equals 0 first. You had your C infinity, you were looking at lines in C infinity. And you were computing Q on all the non-zero points of any line, and you notice that, well, it doesn't matter which multiple of the function you're looking at. So really, the only point that matters on this line, well, minus the origin, is you just pick your preferred point and you evaluate Q there, okay? Because Q is dilation invariant in terms of Rayleigh quotients. So, okay, so you don't really care about one-dimensional lines, you care about a preferred point on the line, something zero-dimensional. Likewise, for p equals 1, you don't care about computing Q on arbitrary two-dimensional subspaces. You only care about looking at these non-zero points of the subspace, mod r star. So in particular here, you would care about something in this circle with this endpoint removed because it's equal to that endpoint. So this is an RP1. This is an RP0. Okay? And so on. So with this in mind, let's go to story 2. So instead of the Laplacian spectrum, now we're looking at Gromov's volume spectrum. And we won't be doing min-max for Q over C infinity. Instead, we'll be looking at min-max for the area functional or the n-1 dimensional volume functional of over hypersurfaces in M. Okay, so some notation here that we'll need is let Z sub n-1 in M with Z2 coefficients. So think about, we don't want to be looking at, it's not good enough to look at smooth hypersurfaces. Earlier we had elliptic regularity, right? So you can take limits, everything is back in the smooth category when you take limits. Here we don't have elliptic regularity, or we're not going to later. So you have to work with a slightly bigger set than just smooth hypersurfaces. So here, take the set of all n-1 dimensional cycles in M with mod 2 coefficients. Meaning we don't look at any orientation. Okay, so here the starting theorem that brings us back to this viewpoint here is something called Almgren's isomorphism. Which is that in that topological space, you can look at any connected component there. So this might be a disconnected space. In any connected component, for example, you can look at the trivial n-1 dimensional cycle, so like the limit of n-1 dimensional spheres as it collapse to a point, just a point. and you can call that trivial cycle. You can see where it is there and take its connected component or any other connected component. So what he proved is that any connected component of this is weakly homotopically equivalent to an RP infinity, like we had here. In particular, we'll be working without loss of generality the connected component of the zero cycle, which I'll denote Z0 and minus 1. All right, so we have our RP infinity. Previously, we had our C infinity, or secretly an RP infinity. We were looking at linear RPPs in that RP infinity. Now we're going to be trying to carry this motivation out here, and we're going to define the Gromov P widths in analogy with the eigenfunction values lambda p. So for p equals, you can take 0, but it's not super interesting, 1, 2, and so on. You can define the p width as follows. Okay, earlier you took the inf over p plus 1 dimensional subspaces, but that was secretly a p-dimensional real projective space. So here we're going to be taking the infimum over all homologically non-trivial p cycles in the space Z0 and minus 1. And for each such p cycle, let's call it capital Phi, we'll take the maximum of all the points sigma in Phi. A point sigma in Phi is a hypersurface, an n minus 1 dimensional cycle with mod 2 coefficients, and it has an area. So we'll take this. This is our direct analog of what we had before. Okay? Now, as I was saying, unfortunately, we don't have an easy regularity theory here. Earlier, elliptic regularity saved us, so we need to replace elliptic regularity with a hard theorem. And the theorem here is due to the following people: Omgren, Pitts, Shane Simon, and Marcus Neves. Who prove that you can set this up, and you can, like earlier, you were able to extract a legit eigenfunction u sub p. Previously, you could extract a minimizing v sub p, and for it maximizing u sub p. Here you can't quite do that. We don't know how to do that. But at the very least, you can extract something that like behaves like that u sub p. So there exists. Earlier, remember, u sub p was a critical point for that Rayleigh quotient q, right? So likewise here, the critical object sigma sub p will be a critical point for area. So there exists a critical point sigma, which I'll call sigma sub p, for area or volume, which means that its mean curvature is, in some weak sense, 0, in case it's possibly singular, which it might be, unfortunately. Now, sigma p may be singular. oh, before that, well, sigma p attains the area. It may be singular. It may, unfortunately, have to come with multiplicity. I'll say epsilon more about that in a bit. And previously, remember, we had our optimal V sub p, the p plus one dimensional subspace, and we knew that modulo that U sub p minimized the Q guy. And we saw that this implies that U sub p minimizes Q modulo a p-dimensional subspace. Here, we don't literally have that, but we have the infinitesimal version of that, which is that sigma sub p has infinitesimally least volume to second order modulo a p-dimensional subspace of perturbations. Which is a fancy way of saying that its Morse index is at most p. I think I saw somebody having a question, but I don't. Okay, well, just feel free to interrupt me if you have a question. All right, there's this. I'm not quite at the notes stage yet. So moreover, in terms of regularity, even though it might be singular, we have the following possible conclusions. So the worst case for regularity, believe it or not, is the two-dimensional case. Here, all we know is that sigma sub p might be a stationary geodesic network. I'll say more about this, so if you don't know what this means yet, I'll say more about this. Geodesic network, let's say with at most p vertices. For n between 3 and 7, sigma p will be smooth. The usual minimal surface regularity theory. For n at least 8, sigma might be singular, but its singular set is reasonably controlled. The Hausdorff dimension of the singular set of this guy is at most n minus 8. And a very interesting theorem, which is not due to them, but it's due to Yang Li and Zihan Wang, is that for n equals 8 and a bare generic choice of a Riemannian metric G, sigma p will still be smooth, like in the previous case. Okay. Now, this is regarding regularity. Also now regarding multiplicity. Here I'll just give the highlight reel that you can sometimes avoid multiplicity. So generically, you can avoid it. That's a theorem of Shinzo that won one of these awards a few years ago. You can also avoid it by a theorem of Dan Kitover, low-dimensional case, Marquez and Neves. But you can't always avoid it, unfortunately. That's another theorem of Shinzo with Zihao Wang, different Z Wang, unfortunately, than the previous one. So Wang, Zhou. All right. So this is what we know, and we don't know that much about the critical objects sigma sub p. I'm sorry? We do not. We have a horrible understanding of the 2D case. Yeah, that's part of why this paper turned out good. Yes? For Almgren pits or for? This is not in this setting exactly. Yeah. All right, so we have our critical objects. We also have a while law, which is due to Evgeny Lokumovich, Marcus, and Neves, who proved that omega p is asymptotic, meaning the quotient is 1 as you go to infinity, to a dimensional constant beta n instead of alpha n times some power of the volume times some power of the parameter p as p goes to infinity. And the only proof of this that we know due to them is geometric. So they actually, it's the idea from the Weil law proof, from Weil's proof of the Weil law, where you decompose into small cubical looking regions. So decompose into small cubes. This leaves, in analogy with the previous story, this begs the following questions. Do we have other approaches or analytic approaches? In fact, what does it even mean to have an analytical approach here? Because earlier, analytical approaches went through Green's functions or the heat kernel. Unclear what this would mean here. Already interesting to think about. Not having analytic approaches and therefore the analytic ideas. We also don't have a refined Weil law. So do we have a refined Weil law? Also unclear. Refined meaning omega p minus that. Can you control the lower order term? And earlier, we knew how to compute the spectrum for a gazillion examples, certainly one per dimension. Here we don't. So on computing what beta sub n is an open question for n at least 3, the case n equaling 2 being the paper from today's talk. So what is... So today is about how beta sub 2 is computable because I'll tell you that we know how to compute this for the case of round two-dimensional spheres. And that will show that this is equal to this explicit constant, square root of pi. In terms of quantum ergodicity, or lack thereof, what do we know? Well, we don't know much, but it's also an open area for investigation. So we know the following, that let's say we're looking at n between 3 and 7, the dimension of the manifold between n and 7. we know that for generic metrics G, the set of smooth minimal hypersurfaces in MG is actually dense in MG. Okay, so you give me any open set in MG, there will be some closed minimal surface passing through. So for generic G, minimal hypersurfaces are dense in MG. And this is due to Iria, Marcus, and Neves. And a very cool result in the 8-dimensional case due to Yang Li and Zihan Wang is that we also know the same result now in 8 dimensions. Okay. So, okay, this is like a partial way to maybe having some partial progress toward the full support analog of Dyatlov, Jin, and Nonnenmacher. Okay, but this is weak. In any case, this is one thing that we know. We also know that due to Marcus, Neves, and Song, that you can construct some sequence of minimal hypersurfaces that does equidistribute. For the same dimensions here. So, and however, Song and Shenzhou also proved that, well, some other sequence of hypersurfaces does not equidistribute. You give me a generic metric and a stable minimal hypersurface, they can find a sequence of minimal hypersurfaces suitably converging to that after normalization. So some sequences do not equidistribute. They call this scarring of minimal hypersurfaces. So so the question of quantum ergodicity here is actually quite open to interpretation, which is good for people who like to not have a specific problem they're trying to solve, but try to do what they can to prove nice theorems. All right. Now let me work back toward the 2-dimensional case. What is the regularity machinery here that makes us keep having to bump into this 3 less than or equal to n less than or equal to 7? So what is the regularity machinery here? It's that if you're trying to study singular points on your critical sigma p in MG, what you usually do in geometric analysis is you blow up at that point and you reduce to the case where you're studying minimal hypercones in flat Euclidean space with index 0, meaning stable. And then you invoke a famous theorem due to Jim Simons that between 3 and 7, the only stable minimal hypercones are the planes. there are no non-trivial stable minimal hypercones. Okay? So this helps you rule out singular points for dimensions between 3 and 7, and for dimensions higher, 8 and higher, you have a machinery called Federer's dimension reduction, which helps you prove you have a low-dimensional singular set. However, we care about the n equals 2-dimensional case. This situation is actually remarkably awful because when you blow up and you get a minimal hypercone in R2, so this is just a collection of rays through the origin whose direction vectors sum up to 0. That is a pretty bad case because all minimal cones in R2 are stable, even the non-trivial ones. Okay? So you can't quite rule out singularities with this machinery. So that's why earlier I said that at best you can prove that you have a stationary geodesic network, meaning you have geodesics, sure, but away from p points where you might have singularities. Okay. In particular, you're worried about the following things occurring. A priori. You're worried about having singular points here and one in the back where this is called a theta graph. So you have your front pole, your back pole, and they're connected by, maybe I should do it like this. Something that does not close up to be immersed geodesics. Okay? Okay, well, thankfully there's at least one improvement here, and that's due to Nicolau AX. He rules out situations like this by proving that, well, he can't rule out stationary geodesic networks, but at the very least, he proves that something like this won't occur because each vertex will have density that is an integer. So here the density is half from here, half from here, half from here, so 3 halves. And he proves that the densities are always integers. However, this still doesn't rule out cousins of this from occurring. Like, for example, you could have 2 things going over here, 2 things going over here, and 2 things going over here, and connecting back. So this now has integer density, and that theorem does not save you. And unfortunately, this is more or less where this story is known to go at the moment. So this is where the following last story comes in about a regularization of the area functional. Double well phase transitions. Which I'll shorten to DWPTs for obvious reasons. So here we want to study a regularization of the area functional, which will hopefully help us avoid situations like these when we do min-max theory. So here's what we do. we take a double well potential. So what do I mean here? Start with a double well. I'm going to call it W because it's standard. So it's going to be a smooth function from -1 to +1 with non-negative values, which is going to satisfy the following properties. So first of all, I'll make it even to make our lives easier, which means I only need to tell you what it does from 0 to 1. And I'm going to make it monotonically decreasing from 0 to 1. So W prime is negative on 0, 1. I'm going to make it vanish at 1. So it's going to go from here to here, and I'm going to make it vanish with slope 0 here. So it's going to be a W prime at 1 equals 0 as well. So it's going to be something that looks like this. Clearly, this is also a critical point because we're even, right? You have to be able to reflect it. And I want this to be a non-degenerate critical point. So W double prime, I'm going to make it be strictly positive. Okay? And I'm going to take this as my potential, and I'm going to feed functions through it in the following way. So for parameters epsilon and smooth functions on M, I'm going to define my energy sub epsilon to be the integral over M. It's a kind of Dirichlet energy weighted by epsilon plus 1 over epsilon times the double well potential applied to my function U. So this is kind of like a Dirichlet energy for U, but I have this extra term that makes U want to stay as much possible away from 0. Okay? Because it would give it too much energy. All right? So it turns out that you can recapture, there's this long story that I don't have time to talk about, that connects double well phase transitions and specifically critical points of this functional with minimal hypersurfaces. So the summary, or what I want to extract from this story is the following, is that for epsilon, well, let's call U with absolute value less than or equal to 1, so that I'm in this regime. Call it an epsilon double well phase transition if it's a critical point for this energy. And so it turns out that we'll also say that if the epsilons go to 0 and we have UIs that are epsilon I double well phase transitions, I'll want to have notation for the following thing. We say that the UIs converge with the squiggly arrow to a hypersurface sigma if their 0 level sets converge to sigma in the Hausdorff sense, say. And if the following measure the square root of the double well potential times the gradient norm times d mu G converges to the area measure of sigma. So I'm looking at critical points of that energy, and I'm saying that I'm taking that critical point and I'm reweighing my ambient measure with this, and I'm going to have situations where then I take a limit, and this it doesn't equidistribute, but it actually converges to the area measure of your hypersurface sigma. So the story here has contributions. I'll just mention the names from De Giorgi, Modica, Mortola, Cohn, and Sternberg, who study minimizers or local minimizers of this, send epsilon to 0, and they prove that the limit sigma they obtain is a minimizing or locally minimizing hypersurface sigma. There's Tonegawa and Hutchison Tonegawa, which study general critical points of this. And Tonegawa, Mikra, Sekara. So let me not mention him twice. And finally, there's Guaraco and Gaspar Guaraco, who set up a min-max theory for this and then send epsilon to 0. Yes? The homology class will always be trivial because of the level set nature of how this comes up. So this is you can construct it in different homology classes, not by looking at real valued functions, but valued in a line bundle that you get to choose. And that theory, Marco Guaraco has started to set up. It's not as advanced yet, but with Z2 coefficients, correct, yes. I don't know that anybody has done anything for Z coefficients, yes. Yeah. Okay. To cut a long story short, you can run a min-max apparatus for this energy, get for each epsilon your critical point, U epsilon sub p for the number of parameters you're doing your min-max over, and you have this theorem of Tonegawa, who proves that in the two-dimensional case, which is the one that we care about here because it's the least well understood, your epsilon I double well phase transitions ui, if they satisfy uniform energy bounds and uniform Morse index bounds, then these UIs will, as before, unfortunately, just converge to a stationary geodesic network sigma with at most p vertices. And even though we regularized our area, our area into an energy, we still don't know for a general double well potential if we can do better than this. The issue with this regularity theory here is that the singularity models now are not just minimal, they're not minimal hypercones in Rn. The singularity models here are the U equals 0 level set of solutions of one double well phase transitions U on R2, i.e. Laplace U equals W prime U on R2 with index finite. And the question is, the singularity model is that is the blowdown the zero level set antipodally symmetric, so that if you have a vertex in your geodesic network and you have an incoming edge, that's one part of the zero level set, will it have to necessarily go out with the same angle to avoid junction points? Yes. Yes, this is my last thing. Yeah. So the theorem that is the technical ingredient is due to Yang Liu and Juncheng Wei, is that if you choose your double well potential correctly, the answer to that is that yes, you can arrange it to be antipodally symmetric. So if you choose W to come from integrable systems theory, which is a valid double well potential, then yes, U equals 0 blowdown is antipodally symmetric. And using this, the theorem with Otis Chodosh is that if you do the two-dimensional min-max theory, the limit sigma is going to be a union of geodesic loops. And if you use this insight, you get the following corollary, that if you compute omega p on the round 2 sphere, it turns out that you just get, well, in the round 2 sphere, you only have equators that are geodesics. So this will only be a multiple of 2 pi. You can compute exactly what multiple of 2 pi you get. You get precisely this. And if you go back to the Weil law, you see that this implies that beta of 2 is square root of pi. So these are the 3 stories that I want to tell you about, like what the various directions are. So I'll stop here. Yes, so there are non-local regularizations that give you non-local minimal surfaces, and then you can send the correspond, which, so that instead of looking at the gradient plus the double well potential, you can look at the fractional Laplacian, and then send the parameter s to 1. And that is another way to elliptically to regularize this equation. And I don't think they can do this for n equals 2 yet, as far as I remember. But that's another, yeah. So Joachim Serra, Figali, and Florid Simon are doing very good work in that direction. No, that avoids multiplicity in no better way than our stuff avoids multiplicity, yeah. For Zmod 3 specifically, you can use not this double well potential. You should be looking at vector valued W's. So you have your minimizers are not just +1, -1. You have like 60 degrees, 120 degrees, and whatever this is. You have your minimizers there, and you can run the machinery there, and you can produce partitions. That's the corresponding analog there. But that theory is very crude. So for example, only about 2 weeks ago were they able to classify the minimizers for those functionals. So it's a very interesting but very crude for now theory, because the vector value W case doesn't have, as earlier, doesn't have the maximum principle. So they have a lot of trouble there. So it's an interesting open direction. But min-max wise, unclear. Yeah, that's something for you.